All right, so we'll get started. So you should see number 6 homework online already, and that's due um, Thursday next week. Tentatively, that day might change. Okay, so it depends on the progress we made in the class. We will make in the class. Okay, so if there's a change, and I can announce it on Tuesday, I think next week. Okay. Um, and then also if there's a change, then exam 2 could be pushed 1 day later uh, on that. Okay. For in-seat classroom disinfection, I assigned to Joshua and Isaiah today. Okay. So we'll be again looking at Gauss's law, some more applications today, but let's take a look on what we learned last time. So we give our definition for electric flux. So electric flux is the dot product of electric field and the area, that's the surface. Magnitude of the A vector will be the area of the surface, and then direction should be the normal direction of it. Okay. So E times area times cosine of theta. The theta is between the normal direction of the surface and the electric field. Okay. That's the definition for electric flux. If you have irregular shape, then you can divide the surface into small patches, and then you can do summation over each small patches for the flux. Okay. And then you can also do that for integration. So if this is an open surface, so then you integrate through the whole surface. If this is a closed surface, you integrate through the whole closed surface. Okay, so this integration sign with a circle just means you are integrating through a closed surface. Okay. All right. And for Gauss's law, it states that the electric flux um, that through a closed surface is equal to the charge Q that surface encloses divided by epsilon naught, the permittivity of the free space. Okay, so that's basically Gauss's law. All right, and then to apply Gauss's law, you'll calculate the flux through the definition. From the flux, you can do integration, or you can do E times A if it's simple, like just you can do E times A. And then you also apply Gauss's law here for flux. So Q phi equal to Q enclosed divided by epsilon. And then you set the two equal to each other, then can solve for E. Okay. So in that sense. I think we looked at a couple of examples last time, but we'll be looking at more applications here today. So for this one, it says find the electric field due to a uniformly charged thin spherical shell of radius r. So that's the gold color shell, spherical shell there. Okay. So we'll be looking at the electric field like in inside the shell and then outside the shell. Okay, I think the two regions there. Okay, so let's take a look here on how you can apply Gauss's law. All right, so last time I think we looked at one example of you have charge distributed uniformly through a sphere, a ball. Okay, now in this case, if you have a shell, then you only have charge on the shell here, right? Inside the shell, you have no charge. While on the last time, the example we checked last time, if this is uniform through the sphere, then inside the sphere, you also have charge, right? Now, in this case, a little bit different. That's the only difference there. So we can see that inside the shell, if you are r distance away from the center of shell, you should have zero flux, right? So in that case, let's say in the region of r less than the radius of the shield, the flux should be equal to, according to Gauss's law, that should be equal to 0, right? Then you can draw a Gaussian surface inside the shield. So if this is the shield has the radius of r, the charge is on the surface, okay, of the shield. Okay, so inside the shield, if you have a radius of small r, okay, or small r there, can you imagine this is a spherical, okay, a sphere, and then outside is also a sphere. I don't think I want to mess up with the outside too much, but just imagine it's a sphere. So then E field over there, all right, on this small sphere of radius small r, that should be equal to E times A, right? Again, if we E times 4 pi r squared, okay? So these two flux, calculating from definition and then calculating from Gauss's law should equal to each other. So you should set up E times 4 pi r squared equal to 0. So that tells you electric field should be 0, okay, inside the shelf, all right? And outside the shelf, for r greater, small r greater than the capital R, so you are somewhere here, you can draw a Gaussian surface, a spherical surface that enclose all this shell inside it, okay? So similarly, this time, according Gauss's law, the phi should be equal to Q enclosed, okay? So in Q enclosed, this time will be capital Q over epsilon 0. Phi from definition E times A, because at any point E field and the normal direction are in the same direction, so it's just E times A should be 4 pi, to be again E times 4 pi r squared. Okay, so you set the two equal to each other. E times 4 pi r equals to Q over epsilon naught. Then E field is equal to Q over 4 pi epsilon naught times r. Okay, but that's outside of the sphere. That's what you get. Okay. Just the difference is inside the shell, you have electric field equal to 0. Outside the shell will be having the same electric field as you have a spherical charge distribution. Okay. Any questions you guys might have? All right. So then if you plot it, this is your E field. Okay. So inside the sphere, inside the shell, its E is equal to 0. And then starting from the sphere outward, you have the exponential decay. Okay. Just like a point charge. Okay. K Q over R squared. Again, that's the same expression for a point charge. All right. So next we are going to check on a couple of other charge distributions and then see how we can determine the electric field by applying Gauss's law. Okay, so this one says you have a thin wire of infinity extent has a charge per unit length of lambda. So line charge density is the green line here. Okay, it has a lambda as the charge there, and it says use this cylindrical Gaussian surface. So that means this guy, this body, this cylinder as the body, its surface as the Gaussian surface. Okay, show that the electric field produced by this wire at radial distance r has a magnitude given by E equal to lambda divided by 2 pi epsilon 0 times the distance r. Okay. You can think about how you would do this as I sketch the problem on my paper here. Oops. All right, so we can first try to see if we can determine the direction of the electric field, right? So let's say if you are at some point, a point, or let me just maybe use a separate line here. So if this is my line, all right, and then if I want to see my electric field at r distance away, right? So I can take a small slice from this line, and then this will be my electric field going in that direction. So this is the electric field, okay? By this small piece, right? Now the fact that this is an infinity long line, you can find another slice that is on the other end over here with symmetry to this line perpendicular to the wire here, okay? You can always find another one that would have a produce an electric field in this direction, okay? Which would tell you that these two, all right, so this is DL, this is DL again, and then the same distance here. So you can see the two electric field will have same magnitude, okay? And then in this direction parallel to the line, they will have components cancel out, right? So you only have electric field that is in that direction as the result, okay? So in that sense, you will see that electric field will be perpendicular to the line of charge, okay, and then pointing away, right? So your electric field should be in any direction over here, should be in just pointing radially away, okay? So radially away there, radially away there, there in the 360-degree directions, okay? Should be perpendicular to this line charge, but away from it, okay? So you can see if you pick a cylindrical body here, then on the side surface here, all right, electric field is perpendicular, or it's in the same direction as the normal direction. Okay, so if that's the E field, the normal direction will be in the same direction. Normal direction and direction. Okay. So for the side surface, you can see the flux should be equal to E field times the area, okay? Because at any point they are perpendicular to each other. And then for the cylindrical, that the wire goes through the center axis, then R is the same. So E will be the same, okay, times A. And on these two buttons here, okay, the left button and the right button here, they are perpendicular to the wire, the same as the electric field is perpendicular to the wire. So electric field and the surface, those two side buttons are parallel to each other. You will get zero flux through those two, right? So then this is the total flux, okay, for this Gaussian, cylindrical Gaussian surface, okay? Now, the area of the side of the cylinder should be equal to, so E times the area should be the circumference of the bottom circle, right? 2 pi times R times the length, okay, of this cylinder you pick. Okay, it could be any length. We just use it L. Okay. Now, according to Gauss's law, flux according to Gauss's law should be equal to Q enclosed divided by epsilon naught, right? For your Gaussian body, the Q enclosed should be from here, the bottom here, to the other bottom on the other side, right? The Q on that portion of it, okay? So then Q will be equal to lambda times the length divided by epsilon naught, okay? So this is a flux from Gauss's law, okay? And then this is kind of from the flux, electric flux definition, okay? So this one will be equal to this one because they are both the electric flux, okay? So you can set up this guy equal to that guy. So E 2 pi R times L equals to lambda times L over epsilon naught. So then you can see the length will cancel out, L and L cancel out, okay? You're looking for E, so then E is equal to lambda over 2 pi epsilon naught times R, okay? And that's the magnitude you are looking for in the problem, okay? I think that should be the same as showing the problem there. So yeah, so you're looking for E equals to lambda over 2 pi epsilon naught times R, okay? All right, so you can see it's kind of relatively easy to calculate your electric field by using Gauss's law, right? If you can also do it from like what we learned before. So if you have an infinity long wire, you can pick this as the origin there, and then a distance away at that point, you can pick a DL or DX if you take this as X axis. You can calculate what would be the electric field due to that small segment in this direction, okay? Because the horizontal direction will cancel out, so you don't have to worry about the horizontal direction, okay? You can do that. You can do integration of K lambda DL over R square, okay? And then integrate from, okay, you'll be writing R as X and then this R, okay? Or actually, no, this is R. If this is R, then you are doing R squared plus X squared, okay? For this distance, this is the distance, okay? And then integrating through from minus infinity to infinity, okay? If you do that, you are likely to get this result, okay? Or you should get the result at the end. But if you are using Gauss's law, then it's relatively easier, okay? All right. So let me know if you have a question on this one before we move on. Okay, so this is for linear charge distribution. If you have a surface charge distribution, then what will be the electric field there? Okay, so let's take a look on this one here. This one says on the green sheet here, you have uniform charge distribution. So sigma will be the surface charge density. Okay, then what will be the E field on both sides of the sheet? Okay, so similarly, in this case, you'll take a cylindrical body over here. Then the surface of this cylinder is your Gaussian surface. Okay, now you have two bottoms and then a side surface. Okay, so similarly, first you want to determine what will be the direction of the E field in this case. Okay, so So on this one, you can imagine, so if you have a surface charge distribution, let me see, maybe easier to put the surface horizontally here, okay? Now, if this is a infinitely large one, you can expect that you divide this surface into small slices, okay? And then you can see if you can find a small dA here, then symmetry to the exit going through the center here. On this other side, you can also find a dA there, okay? And then a distance r away from the surface, you'll see the electric field by this guy will be in that direction, by this guy will be in that direction, okay? So similarly, the x component or horizontal component will cancel out. You'll expect electric field to be perpendicular to the sheet, okay, in that direction, E field, all right? And then if you are r distance away, you should expect the E field to be the same, given that the sheet is very large, okay? All right, so then in this case, you take a Gaussian surface over here, and then also, so you imagine this is somewhere in the middle when they intersect. Okay, distance, this is r away, okay? Now, if field is perpendicular to that, your cylinder is also perpendicular to that, okay? So, so then the flux by this side surface, you can see side surface is parallel to the E field, should be equal to 0, right, in this case. Plus the two bottoms, A times E, okay, so A times E times A, the area for the bottom should be pi r square, or I'm actually not using the appropriate notation here. If this is r, then we may use a different symbol for the radius here. Let me call it A, okay, so pi A square, okay. For one button here, for the other button over here, okay, is plus E, the same pi A square, okay. So then this is your flux. This is 2 times or E times 2 pi A square. You can put that way, okay. Now, for the flux given by Gauss's law, it should be equal to Q enclosed divided by epsilon naught, right? Q enclosed by this body will be just this charge of this surface that is intercept with the cylinder. Okay, so that would be the area of pi, again, A square times the sigma, the charge density, surface charge density over epsilon naught. Okay, so charge surface density times surface area gives you the charge. All right, and then you should set this next one equal to that one, right? Because they are both flux. So then E times 2 pi A square is equal to pi A square times sigma over epsilon naught. The pi A square and pi A square will cancel out. Okay, so the 2 will go down there. So you'll see that E field then is equal to sigma divided by 2 epsilon naught. Okay, so that's for infinity large sheet of charge distribution. In this case, again, you can see the electric field doesn't depend on the distance, okay, that you are away from the sheet. So that means the electric field is uniform on either side of the sheet. Okay. Right. So I think up to this point, we have checked application of the Gauss's law on line charge density distribution, surface density distribution, and then also for the volume charge distribution that we checked in the last class. Okay. Any questions you guys might have on any of these applications? All right, so if not, we will take a look on one example on the application of this. Um, this time we have numbers and then geometry here. Okay, so let's take a look. So it says an infinity thin sheet in the y equal to 0 plane. So that means xz plane. Okay, y equal to 0 plane is this plane. Has a uniform surface charge density of sigma 1 as 65 newtons coulomb over meter square. A second infinity thin sheet has a uniform surface charge of sigma 2. That's 45 nanocoulombs per meter square. They intercept at y equal to 0 and the z-axis. Okay. And makes angle of 30 degree with the xz plane. So the angle between the two sheets is 30 degrees. It asks you to find electric field at this point, 6.0 and 2.0. All right, so let's see here. So you're looking for the electric field at this point, okay, 6 and 2. So the first is to determine if this point is within this angle and this rate is between the two sheets or above, right? So it gives you this angle between the two sheets is 30 degrees. Now you will have to calculate what's this angle, right? It appears to be like less than 30, okay? But you want to make sure, okay? Just double check on that. So then you can calculate what's this angle of theta for the 6 and 2. I'm going to call it theta 1. Okay, so that should be tangent inverse of the y divided by x, right? So if you calculate that, let me see what I get. A tangent of 2/6. So that gives me 18.43 degrees. Okay, so that means you are here. All right. Now it matters because if you have 6 and let's say 6 and 6 maybe, so then you are somewhere here, right? Then you are, this angle will be 45 degrees. Okay, so in that case, so let me just show you the difference here. Okay, so if you are over here, then you have two charges sheets. There will be one electric field in this direction, right, by the bottom sheet here. So you can call that E1. For the second sheet over here should be perpendicular to that sheet but away. So that will be your E2, right? So you have the two electric field in that directions, this one and that one. But if you are above here, electric field by this sheet will be similarly E1 there. But then by this one will be in that direction, the other direction, okay? Will be that E2, right? Because electric field by a sheet of charge distribution is away from it, okay? If this is positive charge, okay? And I think the both charges given here, they are positive charges, so that's true, okay? If a sheet is negative charge, then the electric field are pointing towards the sheet, okay? Just that will be the direction. All right, so indeed we are having this scenario here, not that one, okay? So because you'll be doing vector addition, so then direction matters, okay? In that case, so you're having this scenario, all right? Okay, so then your total E field, your E field, overall E field should be E1 plus E2, vector addition, okay? Now you can see E1 is perpendicular to this guy, so it only has the component that is in the Y direction, okay? So that's Y direction there. This is X, this is Y, and then Z is perpendicular to the plane, okay? And then your E2, so we should ignore that guy because that's not the scenario we have. So E2 here, it should be in this direction, okay? Perpendicular to this guy. Then now you have to figure out what's the directional angle for this E2, okay? So direction for E2, you can determine it's 30 degree there, and then you are perpendicular to it. Okay, this is your E2 direction. So if this is 30, then this is 60, okay? Because it's perpendicular to that. So then you are 60 degree away, below the X axis, right? So your, yeah, or maybe I should call this as sigma 0. So then I can assign sigma 1 to E1 or theta 0 for the angle. I can assign theta 1 to E1, theta 2 to E2, okay? Theta 1 is 90 degree, okay? That's the angle of E1 makes with the positive X. Theta 2 is, in this case, you can see it'll be, it's below, so negative 60, okay? And then for the magnitude, E1 should be equal to sigma 1 divided by 2 epsilon naught, right? We learned that from the previous slide. For E2, it should be sigma 2 divided by 2 times sigma 0, or epsilon 0. All right. So you can calculate E1 and E2, the magnitude. E1 will be equal to sigma 1 is 65 times 10 to the minus 9 coulombs over meter square divided by 2 times 8.85 times 10 to the negative 12 coulomb square meter square times newtons. That gives you 3.67 times 10 to the third newtons over Coulomb. Okay, that's your magnitude for E1. E2 will be 45 times 10 to the minus 9, 2 times 8.85 times 10 to the negative 12. That would be 2.54 times 10 to the third. All right. So then total E, the X component, will be just coming from E2, right? Because E1 is in Y direction. Okay, so it will be 0 from E1 plus E2 X. Okay, E2X will be E2 cosine of theta 2. Theta 2 is minus 60. Okay. So this is 1.27 times 10 to the third. Okay, this is EX, X component of your total electric field. Y component of your total electric field should be E1Y plus E2Y. Okay, E1Y plus E2Y. E1Y is E1 because E1 is all in Y direction. Plus E2Y will be 2.54 times 10 to the third, E2 times sine of negative 60. Okay, that gives you 1.47 times 10 to the third. Okay. Now you have the X and Y component. You can calculate the magnitude of the overall. Okay, so you do EX squared plus EY squared. Okay. So this is something you might want to refresh your memory on vector addition. So then for E is equal to square root of EX squared plus EY squared. Okay, that would be 1.27 times 10 to the third square plus 1.47 times 10 to the third. And then you take square root of it. That will give you 1.94 times 10 to the third. That's your magnitude for the E field, okay? And then direction angle, you want to also figure that out, okay? Direction angle should be tangent inverse of X and Y. No, EY over EX. Tangent inverse of 1.47 over 1.27. That would be 49.2 degrees, okay? Question about this one? Now, if you want, you can get a extra practice. Just try to check what will be the electric field over there. Okay, then you can have some more practice on vector addition again. So in that case, E1 again is just in the Y direction, but E2 this time it be in that direction. Okay, so you'll have different X and Y component. All right. All right. Now we can take another example. This example is on a volume charge distribution. Okay, so it says a uniformly charged non-conducting solid sphere of radius r has its center at the origin and has a volume charge of density rho. Materials removed from the sphere, leaving a spherical cavity that has a radius of b equals to 1/2 of the original r. Okay, and the center over here. Okay, so this is a small sphere being cut out, and then there's a larger sphere there out of the larger sphere. It's asking you to calculate the electric field at point 1 over here, and then at point 2 over there. It gives you a hint that model the sphere with the cavity as two uniform spheres of equal magnitude but opposite sign of charge densities. Okay, so you can imagine this is made of a charge rho sphere. A sphere have a charge rho, and then a second sphere, the same sphere, but charge density of minus rho, right? All right, yes, can take a couple of minutes to think about how you would do this, and then we probably can take a look at the solution together. All right, so you can imagine this is a scenario you have a larger sphere that's a positive rho, right? And then this part is small sphere that has negative rho. So then in this case, positive and negative cancel out becomes a cavity there. Okay, but you can imagine it's made of those two pieces. Okay, a larger spherical with charge density of positive rho, and a small spherical with a negative charge of rho density. All right, so on the larger one, you can see at point 1 here on the surface, you should have E1. You should have E by the positive, right? That is E1 in that direction, okay? Because this is a positive charge, so the electric field is pointing away from it, okay? For the smaller sphere that is negatively charged, so then E field should be pointing towards the charge, right? So that means points inward, okay, by that negative charge, all right? Now if I add a sphere over here, for larger sphere, you can see according to Gauss's law, E1 times A1, the larger area, should be equal to the charge enclosed, right? So the rho, positive rho times V, that's the charge enclosed, divided by epsilon naught, okay? And then for this guy, oh, actually, let's see here. So this would be E1 times, for the spherical area should be 4 pi r squared, right? And then rho times 4 over 3 pi r to the q, all right, divided by epsilon naught. So then this 4 pi and that 4 pi r squared will cancel out, okay? So your E1 is equal to rho r over 3 epsilon naught, okay? And that's in the positive direction. Similarly, for E2, you can take a that small sphere. So then E2 times 4 pi, the small radius, right? Which in this problem it says is B, right? So it will be B. Or actually, in this case, in the first case, the R is A. So A there. In the second case, that's B. So 4 pi B squared equals to minus rho this time. 4 over 3 pi B to the Q over epsilon naught, okay? So again, that 4 pi B squared will cancel out that 4 pi and then the cubic of B. So it tells you your E2 will be minus rho B over 3 epsilon naught, okay? Now your E total will be this guy minus that guy, right, in the X direction. Okay, so E will be equal to E1 minus E2, or E1 plus E2, and then E2 is negative, E1 is positive. Okay, so rho A over 3 epsilon 0 plus minus rho of B over 3 epsilon naught. Okay, be rho over 3 epsilon naught of A minus B for the magnitude. Okay, and then that should be in the X direction. Positive X direction. Okay, because A is greater than B. Okay. Okay. Let me know if you have any questions about this one, okay? So if not, then at point 2 here, this is the center for the big sphere, okay? So the electric field due to the big sphere should be equal to 0 because it's at the center, right? Due to symmetric, it should be 0. So then electric field should be purely coming from this small spherical that has minus rho in density, okay? So the E will be equal to this here, then will be, this time it should be, again, it's pointing towards the center, right? So going in that direction, okay? So that would be the same as this magnitude, but direction should be in the positive direction, okay? Should be rho B 3 epsilon naught, again, in the positive X direction, okay? Because it's purely from the small sphere, okay? The larger sphere will give you 0 electric field. Small electric field will give you the small sphere will give you electric field in a positive X direction, okay? All right. The next section talks about conductors in electrostatic equilibrium, okay? So if you have conductors, conductor has the ability to actually has conduction electrons are free to move from atom to atom, okay? So then that makes them as conductor. So in that case, then charge can be redistributed. Okay, so throughout the body, that means charge are free to move inside the body. So if that's the case, then you can see if you have charge distribute inside the conductor, then they will repel each other because they have the freedom to move, right? So they like to stay away from each other because they have repulsive force among the same charges, okay? So you'll see that the charge will be then distributed on the surface of the conductor, okay? Not inside the conductor, although you have a solid in conductor, but inside of the conductor, you shouldn't have any charge because they like to repel each other, okay? And if you have a charge over here, now if you have a, say, this is like a, probably like a shell, okay, with a very, maybe not that thick, but thickness of certain, like say D. If it's a conductor, then you'll see that it will be induced. So then on the inner surface here, you have negative charge. Outer surface, you have positive charge. But in between the two surfaces, again, you shouldn't have any charge because they are free to move, and then they really like to repel each other for the same charge, okay? And if the charges are induced, so the inner sphere will have negative Q, outer sphere will positive Q, okay? Because in originally its conductor is charge neutral, so then the two induced charges should add up to be 0. And because of that, so that's why if you have metal shoe, you can wear it, you can play with the electricity because you are inside the conductor. There shouldn't be charge inside it, okay? So it should be safe. And then also like the airplanes, it's made of metal for the outside surface. So passengers inside it are safe when the airplanes are struck by lightning. Okay, so that's because you are inside the conductor. Um, the second character of a conductor is the electric field inside it should be 0. Okay, because you can think about if electric field is not 0, then electrons, if the carrier is electron, charge carrier is electron, then it will be under the influence of the electric field, right? Then the charge will be redistributed, okay? So then eventually it will reach the equilibrium point that the electric field inside the conductor should be 0, okay? So again, in that sense, if you are inside a conductor, you are safe, okay? Because there's no electric field inside the conductor. And then on the surface of the conductor, electric field line should be perpendicular to the surface, okay? So again, you can think about if not, then there will be a component that is along the surface for the electric field. So that means the charge there will be dragged by that force, okay? Then charge will be redistributed, okay? So the result should be it's perpendicular to the surface. So then the charge will not be moved anymore at the equilibrium, okay, position. All right, and then if you are inside the conductor, any Gaussian surface you draw should enclose 0 charge, then it should give you 0 flux, okay? So that's again, because of inside the conductor, you shouldn't have any electric field or electric charge. Now, due to that, if this is a conductor, all right, then just outside of the surface, your electric field is equal to sigma divided by epsilon naught instead of sigma divided by 2 epsilon naught, okay? Because for a sheet of metal, you have electric field on both sides, right? But in this case, you only have electric field in one side, okay? So then electric field is all in one side. So then this is twice of a sheet of charge distribution. Remember previously we say for a sheet of charge distribution on both sides of the sheet, electric field is sigma divided by 2 epsilon naught, okay? In this case, because one side you have 0 electric field, it's totally on just one side, okay? The other side, so then outside of the conductor, so then that's twice of that, the initial one, okay? All right. Um, over here, if you have a charge inside a shell of conductor, then you'll see inner shell it will have induced negative charge. Outer shell will have induced the positive charge. Now, if you draw a Gaussian surface in between the two surfaces, right? Then in that case, electric field inside in between the two surfaces should be zero because it's inside the conductor. So E times the Gaussian surface area should be equal to zero. Okay. So then that tells you on this Gaussian surface by this blue curves, the charge inside enclosed should be zero. So that means if you have a charge Q inside this shell, the negative Q induced on the inner surface should be equal to negative of the original Q. Okay, so if say this is 1 Coulomb, then all this negative should add up to be -1. Okay, because total Q enclosed by that blue Gaussian sphere should be equal to 0. Okay, according to Gauss's law. Then in that sense, on outer sphere, you have positive Q. Okay, so this is why on one of the previous slide over here, if this is positive Q, then the charge on the inner surface should be minus Q. Okay, and then outer surface should be positive Q. Okay, because you can draw a Gaussian surface in between the two surfaces that will say it will tell you that the flux should be equal to 0 because E equal to 0. Okay, all right. Now, oh, this one is at the center. So again, similarly, now if you move the charge away from the center, then this the total charge induced on the inner sphere should be also still minus Q. Okay, it wouldn't affect, but you just have density redistributed, right? So over here you might have more dense electric charges. Then over here you may have less charges. Okay, so in that sense. All right, and then I think we will stop here for today.